So good afternoon, everybody. So it's a pleasure for me to be here today. So thank you for the invitation and thank you for the introduction. So in this talk, I will first discuss an overview of what we know about icy moons, and especially the Jupiter's and Saturn's icy moons. And then I will focus on three main moons, which is Titan, Europa, and Enceladus. So let's first start to present the different moons. So here's just a view of the solar system with the Jupiter and Saturn, when you can see the different moons. So in this talk, I will first try to explain you what are the main characteristics of these moons. Do we have a pointer? Oh, here. Okay, sorry. And then I will try to convince you that these objects are very interesting, and I will try to explain what we think we know about their internal dynamics and their consequence for their evolution. So first, the Jupiter system. So Jupiter has about 60 moons, but we are interested mostly on the largest moons, which are the Galilean moons as a function of distance. We have Io, Europa, Ganymede, and Callisto. So the size is respected. So Io has a size similar to the moon, so Europa a little bit smaller, and Ganymede is the biggest moon of the solar system, with a radius which is larger than the planet Mercury. So one of the characteristics of this moon are to have ice at the surface, and ice is stable in this case because the temperature is relatively low, between 90 and 120. And it's only on Io where we can have very large temperature, as we will show later. There is a huge internal energy on Io, and the temperature can be locally up to 1,800 Kelvin, which is very, very large. So we have some good data, relatively good data about the icy moons thanks to the Galileo mission, which was a NASA mission that was sent to Jupiter and reached the system in between 1995 and 2003. So most of the data we have is from this Galileo mission. So I will discuss later in more detail what kind of data we got. So it's just an overview of the main finding we got with Galileo, especially on the interiors of the moons. So the Galileo mission showed that the detection observed an intrinsic magnetic field on Ganymede, which was some kind of surprise. So the magnetic field on Ganymede is larger than the magnetic field on Mercury. Galileo also provides geological and geophysical evidence for subsurface ocean on Europa, so we'll see that in more detail after. And also some geophysical evidence for subsurface ocean also on Callisto and Ganymede. Even if on Ganymede it's not fully sure, but there is some indication. And finally, this data provided gravity data, which provide constraint about the radial profile within the moons of within these moons. For the Saturn system, so here again, around Saturn, we have many moons, like more than 50, between 50 and 60, so a little bit comparable to Jupiter, but there is only few big moons and few interesting moons. And in contrast to the Jupiter system, in the Saturn system, we have only one big moon, which is Titan, which has a size comparable to Callisto and Ganymede. And all the other moons are much smaller. And so I will not detail all these moons. But one moon of interest will be Enceladus, which I show you here, which has a size 10 times smaller than Titan. And even if it's a very small moon, as you will see, it's a very active body. So here again, the temperature of the surface is low enough to have ice stable at the surface, and as you will see also, it's low enough to have liquid methane in the case of Titan. And it's only the case of Enceladus where we can have some increase of temperature locally due, again, to internal heating, and we can have up to 200 Kelvin at the surface in very localized place. So for the Saturn system, we have a lot of data now thanks to the Cassini-Huygens mission, which is in orbit around Saturn since 2004. So the mission is still operating now, and it will end in 2017 by doing a final dive in Saturn. So one of the important events of this mission was the descent of the ESA-Huygens probe in 2005, which measured for the first time the composition of the atmosphere of Titan and revealed this surface. And since that time, we have regular flybys of the different moons. And for the case case of Titan, I think we reach about 100 flyby of Titan and several tens of flyby for Enceladus and other moons also, but I will mostly focus on Enceladus and Titan here. So the main discovery of the Cassini-Huygens was first the discovery of active jets at the south pole of Enceladus. Here is a recent picture of it, which is pretty impressive. So we can see jets coming from a fracture, which is very hot fracture, I will show later. We have also a discovery of an active methane cycle on Titan, which is comparable to the water cycle on the Earth, where we observe lakes. Like here, we have a view of the North Pole where there is big lakes, which is not lakes, it's seas, because it's pretty big. And we observe also river, thanks to the during the Huygens descent, and also clouds, which indicate that there is an active cycle at present. We have also some geophysical evidence about ocean in Titan and Enceladus. I will go in more detail in case of Titan later on. And we have also evidence of chemical exchanges with the interiors in both Titan and Enceladus. On Titan, it's probably during the past, but Enceladus is operating at present, and we can directly sample the interior of Enceladus by flying through these plumes. So here is just a summary of what are the main evidence of activity on this moon. So the three most active bodies are Europa for Jupiter, and Enceladus and Titan for the Saturn system. So now I will focus mainly on these three moons. So on Europa, the main evidence are the discovery of salt materials related to tectonic features all over the surface, which indicate that there is some kind of exchange processes with the interiors. And we have also evidence from the magnetic field observation of a conductive layer, for which the best candidate will be a salty ocean. So these indicate that there was some chemical exchange through this ice shell, and possibly by the help of convective processes. And the salt also indicate that there was water-rock interaction during the evolution of Europa. In the case of Titan, we also have a very interesting observation that was made by Huygens, which is the observation of argon-14 in the atmosphere of Titan. And this argon-14 indicates that there was an exchange with the rocky part of Titan. So we know now that there was, at least at some time during the evolution of Titan, we have some internal outgassing, which may explain the methane we observe now. There is also evidence of a salty subsurface ocean, which is provided by a combination of geophysical evidence, so from tides, obliquity, and electric perturbation. So I will go in more detail after. And we have also evidence of methane in the atmosphere on the surface, which indicate that there was some kind of reprocessing of the methane during the evolution of Titan. And finally, in the case of Enceladus, we have this very impressive jet, which clearly indicates that there is activity at present. And this jet is emanated from this fracture here, where we can observe directly with, in the infrared, Cassini was able to directly observe the heat coming from the interiors. So here we have elevation of temperature of 200 Kelvin, which is pretty large because the average temperature on Enceladus is only 60. So we have a strong increase of temperature very locally. And thanks to the in situ, the mass spectrometer and the dust analyzer on Cassini, it was also possible to directly analyze the composition of these plumes. So now we know that there is salt within the icy grain that is emanated from the south pole of Enceladus. And we also discovered different molecules, and especially organics molecules, which indicate that maybe there is some complex macromolecules in the interiors of Enceladus. So after this rapid overview of the different discoveries on Cassini, I will now go in more detail about what we can learn about, what we can say about the evolution and the dynamics of these moons. So if we want to understand the evolution of these moons, we need to know better what is the interior structure of these moons. We also need to have some indication about what is the source of energy that creates the activity. And finally, we need to understand what process control the chemical exchanges. So I will try to go briefly during this talk about these three main points. So let's start with the internal structure. So the main data we have is provided from the gravity field measurement. So this was done from Jupiter by Galileo and Saturn by Cassini. So from the gravity field, we can estimate the moment of inertia. I will go in more detail after by illustrating the case of Titan. So it's just an estimation of the moment of inertia. So from this moment of inertia, we can see that there is a relatively large variation of the moment of inertia depending on the moons. We can have moons like Ganymede where we have a strong, very small moment of inertia, which indicate a strong concentration of mass toward the center. And at the inverse, we can have moons like Callisto, which has similar size and superior density, where the moment of inertia is much larger, which indicate a very weak differentiation. So another important aspect is also to consider, we know that there is water ice inside these bodies, especially based on the density. We know that the density is about, for instance, for this case, about 2, which indicate that there is about half of the mass which is provided by rocks and the other half by ice. But so we have some, we know from laboratory studies what is the phase diagram of water ice. And the particularity of these moons is the fact that the pressure for the biggest moons is large enough to create high pressure ice, which means that in the case of Titan, Ganymede, and Callisto, which are the biggest moons, the pressure is large enough to have, so we can have an ocean, but the ocean will be trapped between 2 ice layers, which will be very different in the case of small moons, like for instance the case of Europa on Enceladus, where the pressure is lower. In this case, if we have an ocean, the ocean will be directly in contact with the rocky part, which has different implications for their evolution. So it's just an overview of what we think are the internal structure of these moons. So based on the moment of inertia and based on the magnetic field detection we have on Ganymede, we think that there is, we are almost sure that there is an iron core in the interior of Ganymede. In the case of Callisto, we know that the moment of inertia is large, which indicates that there is not a full separation of rock and ice, which is still a mystery. And in the case of Europa, we do not have a direct evidence of iron core, but we believe there is an iron core and a rocky core. And in the case of Titan, we don't really know if there is what is the size of the core. I will discuss this in more detail afterward. So from the data, we have some idea of the structure, but we still don't know what is the relative thickness between the ice layer and the ocean. We know that there is an ocean because we have the inductive magnetic field, but we don't know what is the thickness of the ocean and the relative thickness between the ice layer and the ocean. And we have also very poor constraint about the size and density of the rocky core. So really just in more detail in the case of Titan, just explain in the way we can constrain the structure. So Titan is the body for which we have the maximum geophysical observation. So it's the one for which we can say the most about the internal structure. So we have measurement of the gravity field up to degree 3, which is still low, but still it brings some insight about the interiors. So classically, we use only the degree 2 to infer the moment of inertia. So this is the classical assumption that is done for all the other moons, where we have only the degree 2. But in case of Titan, we can test a little bit this assumption. So if we assume that the degree 2 is mostly determined by the fluid dynamical flattening, we can directly related the moment, the C20 to the moment of inertia using the well-known Rado-Darwin approximation. So if we do this exercise in the case of Titan, we end up with a value of 0.34, which indicates that Titan is not really differentiated. But after, we can see that there is not a full, Titan is not fully at the hydrostatic equilibrium because we have a significant degree 3, and also because the degree 2, 2.0 and 2.2 are not exactly, the ratio is not exactly equal to what we expect for hydrostatic equilibrium. So this indicates that maybe we have some departure from the hydrostatic equilibrium. And this is especially indicated by the topography. So from the topography, we know that we have a strong variation of the shape of Titan. And this strong variation, the altimetry is of the order of 400 meters, which looks not very big. But if we compare to the flattening, it's pretty large because the flattening is only 100 meters, which means that we have a relatively strong distortion of Titan relative to the hydrostatic equilibrium. So this indicates that there is probably large variation of ice shell thickness. And if we have large variation of the ice shell thickness, this may have impact also on the interpretation of the gravity field. So the other constraint we have is provided by the time variation of the gravity field. So in the case of Titan, the gravity the variation of the gravity field was large enough to determine the K2 number. So it's the first time we have this measurement for icy moons. And we have also indication, an observation of the ubiquity, which is 0.32, which looks small, but in fact it's pretty large compared to what we expect from the theory. Normally, it should be 3 times smaller. So these two information indicate that there is probably a liquid layer that decouples the outer ice from the deep interiors. And finally, there is also evidence from Cassini against constraint that show that there is an electrical conductive layer at depth. So it's not a magnetic induction. In this case, it's an electric perturbation in the atmosphere, which is called Schumann-like resonance. So I will not go into much detail. So if you want to explain the obliquity, we can use models. So this is, for instance, a model that was proposed by Rosemary Balland, where she showed that the large obliquity of Titan can be explained only if we consider decoupling between the different interior layers. And in addition, as I showed before, we know that there is probably variation of the ice shell thickness. So then we include also the variation of ice shell thickness to see how this impacts the equilibrium of Titan and how does it impact the equilibrium obliquity. So once we take into account all the different constraints, so for instance, the obliquity, the degree 2 surface shape, and degree 2 gravity field of Titan, as well as the K2 love number, we try to compute what internal structure can explain all this data. And we realize that, in fact, the obliquity is a pretty constraining quantities, and we can explain the obliquity only for very specific interiors. And we show that, in fact, if we want to explain K2 and the obliquity, there is only a few interior structures that can explain all the data together. And we tested like 900,000 different interior models. Only 50 models fit the data. And so here is all the data that can fit, and we can see that the data depend on the K2. So we can have a relationship between the K2 and the moment of inertia. So from this measurement, we have the K2, so we can infer what is the acceptable range of moment of inertia. And we can see that, in fact, the moment of inertia could be as low as 0.31, which is pretty far from the simple estimation that was done from Rado Darwin. So this indicates that probably Titan has a very dense ocean, so it's one of the output of this calculation. And it also indicates that, in fact, we don't really know what is the differentiation state of Titan, and it could be as low as 0.31, which is comparable to Ganymede, or as large as 0.35. So there is still large uncertainties about the rocky part of Titan, and I'm not sure we will be able to solve this issue before we send a seismometer on Titan. So it will be in the next century, maybe. So now let's move to the heat source problem. So as I mentioned before, we know that there is a huge heating in some moons, especially in the case of Io and Sladus. In the case of Io, we estimate the total power emitted from the different volcanoes. It was estimated from Galileo to about 100 terawatt, which is more than 2 times the internal energy of the Earth. So this, in the case of Io, it's 100 times larger than the expected radiogenic power. So this indicates that there is a strong energy, and the most likely source is tidal heating. And on Sladus is the same. We have a huge hotspot at the South Pole. So it's pretty small compared to Io. It's only 15 gigawatt, but for Enceladus is very large because, once again, it's more than 10 times the radiogenic power. So this is due to tidal heating, so we have a pretty good understanding of how tidal deformation works. So it's related to the fluctuation of the gravity field during the travel around the main planet. So because there is an eccentricity, there is a change of the tidal forces. And because also of it's not perfectly circular, there is also a change of the elongation. So we have a permanent flattening and elongation, but in addition, because of the eccentricity of the orbit, we'll have a periodic modulation of the flattening and periodic modulation of the elongation, which create deformation, and part of this deformation will be dissipated by dissipation, and will create heat. So in fact, we believe that there is different mechanisms that can generate friction. So it's just a cartoon that shows you all the different mechanisms that's been proposed. So we can have dissipation, for instance, along the main tectonic fault, for instance, in the case of Europa. So we know that along the faults we can have a strong friction, and locally the temperature can increase. We can have also this viscous dissipation distributed within the entire ice shell, if the ice is warm enough and have a sufficiently low temperature. And we can also expect some dissipation in the silicate mantle, dissipation of the core of between the iron core and the mantle, also dissipation due to resonant Rossby waves in the ocean. So this is the different possibility that's been proposed. I personally believe that the maximum dissipation is in the ice shell, but it's possible that there is also other source of dissipation. In the case of Enceladus, there was a different study that has been done to try to estimate what is the main source of dissipation. There was a study about the possible dissipation of tidal waves. So these studies done by Terre show that it's possible, but this occurs only for very specific range of ocean thickness, and it's only for very thin ocean, which is not very likely. In the case of viscous friction along tiger stripes, so the main fault that we observe at the South Pole, it has been also computed, but this can be significant, but only if the tidal motion is very large, which requires a very big ocean, which is also, again, not very likely in the case of Enceladus. And if we calculate the dissipation within the ice shell, we can show that this can create a lot of energy, especially in the warmest part of the ice shell at the South Pole. And for this, we don't require a big ocean. We just require the existence of an ocean because we just need to decouple the ice shell from the rocky part. But as long as there is a liquid layer here, it works. And we don't need a global ocean. Only a localized ocean will be enough. So in order to understand in more detail how the heat generated is in the interior of Enceladus and how it's transported to the surface, we have developed a new tool in 3D that computes simultaneously the thermal convection. So it's based on the model Oedipus developed by my colleague Gabriel, and it's coupled to a model that computes tidal dissipation in 3D that was developed by my colleague in Prague, Andrzej Czadek. So we have coupled this model, and now we can compute in a self-consistent way the production and the transport of heat in the interior of Enceladus. So it's just an example of calculation. For the moment, we don't know what is the size of the ocean, so we try to calculate what will be the influence of this internal ocean on the ice shell. So there is just a computation assuming there is an ocean only in this part, here for this part or this part. And then we calculated what should be the eccentricity in order to create huge dissipation. So if we calculate the dissipation at present with the present eccentricity, we end up with a relatively low power, which indicates that maybe there was a larger eccentricity in the recent past. So we try to compute what should be the eccentricity in order to reach significant production. So we can see that we need either 2 times the present eccentricity, 4 times, or 10 times, depending on the size of the ocean. And we show that, for instance, in this case, when we have 2 times the production, 2 or 3 times the present eccentricity, we see that the temperature increases very rapidly. And we show that we reach the melting point and we generate a lot of melt. And in this calculation, we show that the melt can, in only 1 million years, we can generate like 7 kilometers of water, which will create rapidly an increase of the ocean and then a strong, generate strong stress within the ice shell. So based on this calculation, we propose a possible evolution scenario for Enceladus, where we expect that so this is the diagram that shows you the tidal power as a function of eccentricity, just a cartoon. But during period of low dissipation, the eccentricity will increase because it will transfer angular momentum from Saturn to Enceladus. So we increase the eccentricity. So as we increase the eccentricity, the tidal forcing will increase until we reach a critical point where melting will occur. And when we create these melting events, we'll generate strong stress within the lithosphere. So we break the lithosphere, and when we break the lithosphere, we can start to cool the interiors very efficiently. So the temperature goes down, and the tidal power will go down, and then we end the cycle. So we predict with this model that we should be at the end of this cycle at present. So it's a prediction. So we will test in the future to see what should be the periodicity of these events. We estimate between 1 or 10 million years, between 10 and 100 million years, but it's just a possible evolution scenario. So now just to rapidly, what is the time? 10 minutes, okay, that's perfect. So I will now switch to the third aspect of the evolution of the moon. So it's what is related to the exchange processes between the interiors and the surface. So as I mentioned before, we have several evidence of exchange processes. So here again, we have this eruption activity on Sladus. We have the salt deposit correlated to tectonic features on Europa. And we have the argon-40 on Titan, which indicate that even if there is no outgassing activity now, there was some outgassing activity in the past. So we'll mostly focus here on Europa, because before I consider Titan and Sladus, and now I'll move on Europa. So on Europa, one question concerned the possibility to have liquid water near the surface. So we know, we're almost sure that there is an ocean at depth. We don't know exactly how deep is this ocean, but there is also some speculation of localized liquid water near the surface at maybe only a few kilometers, which is very interesting, because we can expect that in the future we may be able to detect this perch liquid reservoir. So the idea here of this study was to test what is the stability of such reservoir in the case of Europa. So there is two contexts where water perch reservoir has been proposed. There is, for instance, in this case of terrains, which is chaotic terrains, where we can see that there is some kind of depression. So this has been interpreted as the presence of collapsing melt lands just below here that should be still present now. So this may be related to a tidal concentration within a thermal plume. So it was a model we proposed with Christophe Sautin a few years ago, and then this idea has been used again to explain this kind of features. So this is one context where we could expect some water. There is also some indication of deflection around this double ridge. So double ridge, it's these typical features that we observe almost everywhere on Europa. In some places where we have high resolution data, there was some deflection, which has been interpreted as a possible presence of a seal below these features. So the idea of the study we did with our colleague in Prague, with Karla Kalusova, which was a PhD student between Nantes and Prague, was to test what could be the duration of such shallow melting events, and what could be the amount of accumulated water we could expect within an ice shell. So to test this, we use different contexts. So as I mentioned, there is two kind of way of generating melt in some places. We can have generation of melt that was proposed by Nemo and Gaidos, which was just at just below a tidally active strike-slip fault. So in this case, if the deformation is large enough, we can reach the melting point and generate some melt. And we can also generate some melt, for instance, at the top of thermal plumes, which is heated by tidal dissipation. So in order to test the production and transport of this water, we develop a new two-phase model that includes water production and porosity advection, asymmetric compaction, and the temperature evolution of the system. So here I just show you some simulation that was done first in a simple case where the temperature is constant within the entire model. So we are at the melting point everywhere. So this is just to test what is the dynamics of the system. So here we consider an ice layer of 30 kilometers thick, and we assume that there is a production region of melt here. So this is calculation done for different permeability of the ice, so which is the typical value we expect from ice we have on Earth. So we can see that the patterns will be a little bit different depending on the permeability, but in all cases we have a relatively fast collapse of the liquid lens. Here, for instance, the water generated here will reach the base of the ice layer in less than, so it's 0.2 kiloyears, so which is pretty fast. So then after it depends a little bit of the permeability, which is natural, but still it's always very fast. So it's just another test where we consider different threshold melt in order to start the percolation. But here again, we have a relatively fast percolation of the water, which is not a surprise, but we needed to do this calculation to convince people that just to simplify model, that maybe you need first to consider this the instability of the layer before proposing something that is not fully feasible. So then we consider a more realistic context, which we consider the variation of viscosity as a function of temperature in addition to the melt production and the transport. So it's just a typical simulation that corresponds to a plume that develop with tidal heating. So this is the tidal heating field and it's the plumes. So we can see that at the beginning the plumes develop. We have reached some point, we have some melting within the plumes, but the melting increase as a function of time, and at some point the melt will create a collapse of the plumes, and the plumes disappears after about 100 kiloyears. So with this calculation, we show that it's almost impossible to accumulate a large amount of melt. We never reach more than 1 or 2% of melt locally in the ice shell. And even if we put some melt at the top of the ice shell, it never lasts more than 50 kiloyears. So if there is really water length in the ice shell of Europa, this means that it's very recent and it's related to very intense heating episode. It cannot be all over the surface. And then we did a similar calculation in the context of strike-slip fault. So here again, we have production of melt here just at the base of the fault, and we have a progressive increase of the temperature because of the strong dissipation along this fault. And then we start to create some melting, and then we have a progressive collapse of the water toward the base of the ice shell. So in this case, because the system has a higher viscosity, this is much slower, but still we can see that we always have a progressive disappearance of this liquid layer. So there again, that indicates that it's pretty difficult to have liquid near the surface, except if it's in the context of very cold and conductive layer, which is in contradiction with the existence of liquid. If it's very cold and conductive, it will be difficult to have significant dissipation. So it's just a work in progress. So now, if we really want to understand the dynamics of the ice shell of Europa and Sladus, we need to consider many kind of process before being able to really understand what happened in this kind of object. So in the future, we plan to incorporate, for instance, the fracturation of the upper lid, which will be a key processes if we want to understand the exchange between this convective part and what we observe at the surface. We need also to better understand all the process of compaction of porous layer, because we know that on these moons there was a bombardment from meteoric bombardment for billions of years, so we can expect there is a porous layer at the top in the upper part, which may have a significant effect on the thermal evolution of the moon and also on the mechanical behavior of the moon. So this is a key aspect. And we need also to better understand the transport and neurological feedback between due to the presence of non-ice material, like for instance salt or other like clatrate compound that may affect the dynamics of the ice. So this is to be continued. So just to conclude, so this is for the modeling part. For the observation, we'll need to wait the next generation of exploration. So now the next exploration will be done by the JUICE mission, so the Jupiter Icy Moon Explorer, which has just been adopted by ESA, and which should reach the Saturn system in 2030, and will be in orbit around Ganymede in 2032. So there will be also two close flyby of Europa that will also maybe provide some new data to constrain the dynamics of the ice shell and the possible exchange with the ocean. So we need to be really patient. So thank you for your attention.